Hi there, in this recording I'm going to describe um, the PySpace solution to nonlinear acceleration. Um, in a weak gravity field we have linear acceleration, and in a very strong gravity field and at relativistic speeds it's been shown in special relativity that the rate of acceleration falls off, and that you can't hit the speed of light. In a previous lecture I explained that the Lorentz-Fitzgerald transformation could be explained using a series of cos and sine combinations. So the formula for the Lorentz-Fitzgerald transformation is the cos of the arc sine v over c. So, and I've shown that it is also represented by spheres or pi shells. So the next stage in the advanced formulas is to describe how to explain nonlinear acceleration in the PySpace theory. The advantage of the theory is that when special relativity was developed, only velocity was considered, and all the examples typically in special relativity are to do with velocity. They're not to do with acceleration. Acceleration was seen as a different case, and Einstein moved on and he worked on a theory called general relativity, where he developed tensor calculus to describe that. Now that tensor calculus is quite complex, so the PySpace is another way to explain relativistic acceleration. So the purpose of this lecture is to describe how to explain nonlinear acceleration, which is relativistic acceleration, without using general relativity, and by essence extend the special relativity work. This is called the PySpace theory, but you can think of it as an extension of the special relativity work. So let's just consider what acceleration is first. It's the rate of change of velocity with respect to time. This is the Newtonian formula. Works quite well in a weak gravity field such as the planet Earth and most planets. It works quite well. Obviously we know if you're in a collapsar or a black hole it doesn't really work. But let's move on to the next idea in PySpace. In PySpace, what we're looking for is a formula that extends the existing acceleration formula, but keeps the original one. Rather than throw away what's already there, let's extend what's already there. So in the PySpace idea, we're going to have this formula which it works for both v much less than c and v less than c. So in other words, you could be near the speed of light, and you want let's say you're at 0.8 of the speed of light, and you accelerate up to 0.9. The acceleration there is nonlinear. How do you model that? If you have these numbers, how do you model it? So the idea behind the formula is that when you have very small values for velocity ranges, such as 0 to 20 miles an hour, such as in a car, if you plugged this formula in with the gamma value, it should come out as 1. If you're at a higher velocity near relativistic speeds, it should be less than 1 and close to 0 near the speed of light. Pretty much the 0 at the speed of light. So when there's virtually no acceleration, the gamma value is 1, and when you're inside a weak gravity field, the value should pretty much be 1. So let's look at the mathematical formula for deriving this, and this is advanced PySpace. So So I've already explained in other lectures that you can use, if you're not sure of this, you'll have to look at the other lectures. But basically, what we use is we use cos and sine to represent. Cos represents compression or the loss of area of a sphere. That's due to movement, and sine represents the increasing area loss. So you have a sphere which is an observer sphere. You have another sphere which represents the increasing speed, and you subtract those two areas. And in pi space, you use cos and you use sine. Cos for compression, sine for the gaining of or the increase in an area loss value, and then you also use arc sine, as I've explained before. Arc sine maps v over c from 0.0 to 1. It maps it to 0 to pi over 2. So what we're doing is we're using the natural values that come out of these formulas to determine what the gamma value is for acceleration. So let's apply them to this formula. So we have the gamma value, which represents we have two velocities. So typically an acceleration is defined by two velocities, a velocity range, and in the case of the pi space theory, the sine component represents the gain in the in the size of a sphere, and that represents the area loss. And in pi space, the way it works is when you move faster, you lose area. So the sine arc sine component represents the actual area loss. So what we have here is we have gamma is the sine minus sine of the larger velocity minus the sine of the smaller velocity divided by the velocity range itself. So what we're essentially trying to do is calculate a slope. All right. So the idea is pretty simple. If you take a look at the sine curve that you draw, typically you'll find that at the lower values of the inputs, you'll find that you get a slope equal to 1. In other words, the rate of change of the slope at the lower values is essentially almost linear. Now this maps to the concept in a weak gravity field that you have linear acceleration. So in other words, if you drop something from height in a weak gravity field, typically the acceleration is linear. Now as you go further, as you move to higher speeds, the change is nonlinear. So what you can do with this idea in pi space is you can put in the sine and the arc sine here from the this is a Mathematica expression, and you can put this expression in yourself, and you can plot the nonlinear nature of the curvature. What you see here is that from 0 to about 0.2, you can see here that this is 0.2, say of the speed of light. You can see here that it's pretty much linear, right? So right here to here, it's pretty linear. So that would be 0.1 of the speed of light. That would be sorry, that's 0.2, so that's 0.1. So you can see that the idea would be that in here, in this section here of the diagram, that this is kind of like your car. You see this tiny spot in here. That would be like a person on a car accelerating from, say, 0 to 60 miles an hour, or it would be a person falling under a weak gravity field. This is the degree of area change that would be experienced with respect to time, a very small amount of area change. This would be a spaceship trying to accelerate, and so on. So this slope here represents the gamma value as it's calculated. So let's take a look at the values. If we do a table in Mathematica, you get the values here. So just to understand what you're looking at here, this is the formula, which is the sine of the arc sine of 0.1 to 0. So in other words, it's a delta. So it's like 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3. So if we look at the Newtonian way of calculating it, every time you'll get 0.5, 0.5, 0.5, 0.5 every time. Okay, because you subtract the 2 and you divide by time and you get 0.5, right? So that's all good and well, and that's the Newtonian one. So that's the linear acceleration, and it works under weak gravity field. Now in pi space, what you do is you multiply the result by the gamma value, and in the case of 0 to 0.1, you get 0.99829, so you get almost the same value back. And what you notice is as the range of values goes up, you see that the gamma gets smaller. Okay, so for example, if you look at traveling from 0.9 to 0.1, which is the speed of light, you see that the gamma value is 0.22. So in other words, the acceleration's falling off as you reach higher velocities. Now, if you put in 0.9 to 999 to 0.1 to 10, which is the speed of light, you put that into the formula, you can see that pretty much you get 0. So in other words, there's virtually no acceleration near the speed of light, right? And the way we calculate that is what we say is that if we model acceleration on an area loss of a sphere, and we use the pi space formulas, and we multiply the traditional value by the gamma, you see that you can't keep subtracting area from a sphere that has almost no area, and that's essentially how acceleration is perceived in pi space. Now, there is a more complicated way to do it, which is you can use an integral summing up the averaging of all the slopes, and you can assume delta x is 0.01, and so you can do it that way if you want. You can use the numerical integration, which is a mathematical expression, and as you can see that you get the values as you go closer to 0.9 and 1.0, that the values are almost 0 there too. So basically, the way pi space calculates it is it extends the Newtonian acceleration and adds in a slope factor to do with the range of the velocities. So let's just go through the proof real simple, real quick. If we consider an object with velocity v1 accelerating to v2 over t time t, the acceleration is the rate of change of velocity with respect to time. So in pi space, acceleration is the rate of change of pi shell area loss, which just means sphere area loss or atom area loss with respect to time. In pi space, the change of area of a pi shell or atom is modeled by the sine x function. That should be arc sine x function. Representing per second area change in terms of its diameter, and then the diameter line represents the velocity v over c, and the angle represents time t per second time t, and therefore for 0 to 90 degrees it represents a pi shell accelerating from 0 to v over c time t per second. So what we have then is we have from differential calculus, acceleration is the slope of the velocity change, and the slope is the sine x function between v over 2c and v1c, which represents acceleration. And then we can turn v over v2 divided by c and v1 divided by c into an angle using the arc sine function. And then we can calculate the slope, which I've discussed already. One needs to add the slope at each point and add them up and average them over the range of velocities under consideration. And then you can use an integral to add up the individual y-x slopes. Then we divide the summed slopes by the range of angles to get the average acceleration over that range. And so in this case, where v is much less than c, we can subtract the velocities and divide by the angle difference, which is equivalent to time. So essentially, all we're really doing is calculating the slope of the area change, and the way we do that is we use the sine function, and we do some integration, and we divide by the range, just like you would in any kind of basic calculus example. So the really nice thing about this idea is that you still keep you still keep the acceleration formula defined by Newton, and you just add this scaling factor here, gamma. And that's the really nice part about it, that you can that you scale the acceleration based on the velocity range. So the idea is really simple, that you take the velocity range, and the velocity range defines the slope or the actual scaling back factor. So in other words, if that's like 0 to 20 miles an hour, which is 0 over c and 20 miles over c, the gamma will always be at 1. So you just get the Newtonian result. Later, I'll show how maybe we can apply that gamma to the more well-known Newtonian formulas for distance and speed and position. Alright, that's it. Thanks very much. Finally, there's a page in the theory which shows examples of how you can apply it. So that's it here. This is the non-uniform gamma. So this is in the PySpace theory page, pyspacetheory.storytelling.com, and I try to show how you can apply it to different formulas. Thanks very much.